All right, today we are starting a new unit, and that new unit is work. It's work and energy. Now, when we say work in physics, we mean something differently than we mean when we say work every day. Doing work every day, well, you guys know what you mean by that. But work in physics is something specific. So for us, doing work is using a force to move an object. All right? If my force moves an object, I'm doing work. If that force does nothing to move an object, I'm not doing work. So, today we are going to understand this definition of work, including when it's positive, negative, and zero, so that we can calculate work. We can calculate work from a constant force. We can use a graph to find out work. And then we can calculate work done on an object when we're applying forces at weird and different angles. So, let's get into it. And again, mechanical work is different than work we have in everyday life. So, for us, work is, like I said, using a force to move a distance. So to calculate work, we're just going to take a force and multiply it by how far we move. So let's do a simple example. Let's say I have a mass of, I need a thinner pen, 1 kilogram. And to that mass, I apply a force of 10 newtons, and my object moves in this direction a distance of 5 meters. That's my delta x. Now, we know from our forces unit that we have a normal force acting straight up and weight acting straight down. So let's talk about the forces that are doing work on this object. The 10 Newton force, does that do work? And the answer is yes. The 10 Newton force acts to move it this 5 meters forward. So let's circle that. Yes, we do work. Hooray. The normal force, does that do work? Does this force have any contribution to moving this thing forward at all? Well, I'm going to say no. Because that force is acting up, but the thing is moving to the right, so that doesn't do any work at all. Same thing with the gravity. It's in the wrong direction. It's not contributing to the movement of my object. So, if I want the work done on this thing, I have the force in the direction of motion, 10 newtons, times 5 meters. So the work done on this object is going to be 50 Newton meters. Well, a while ago, physicists decided that that was hard to say, so we're going to say that it is 50 joules. Joule is our unit for work. One joule is 1 Newton meter. So, we're going to talk more specifically about this positive and negative work thing. So, the first thing that's different about work is that it is a scalar, not a vector. So it doesn't have any direction associated with it. And that means positive work and negative work mean something differently than going forward and going backwards. Okay? So, let's take two objects. Object 1 and object 2. And let's say that both of these objects move forward. But let's say I apply a force to this object that pushes it forward. And at this object, I apply a force that doesn't push it forward. That force slows it down. We're going to look at what each of these things mean. And what we're going to remember is that work is using a force to move an object. Okay? Now, in this case, right, I'm pushing forward, the object moves forward. Okay? We know that that thing has to speed up. The force moves the object. Okay? That's going to be positive work. The force is actually doing something constructive. It's making the thing go forward and it's speeding the object up. That's positive work. Force is in direction of the displacement. Here we have negative work. With negative work, this force isn't helping me out. If I am moving forward, which means I have a forward velocity, and I apply a backwards force to it, we're slowing it down. The force is slowing my object. Well, that's the opposite of moving the object. That's the opposite of speeding it up. So we're going to call that the opposite of positive work. That's negative work. That's force opposite displacement. That's negative work. My object slows down. That's not helping me move forward. That's positive and negative work. Now, we have one more thing to talk about. What if we pull on our object at an angle? Okay, if we pull on our object at an angle, but the object still moves forward this way, we have two pieces of our force to deal with. Okay, we have the part of our force that's in the horizontal direction, and we have the part of our force that's in the vertical direction. So looking at both of these, this one right here, force in the vertical direction, doesn't contribute to this motion at all. So that's not going to do any work. Does no work. That force does not move my object. That's going to have a consequence to the normal force between the object and the ground, but that's not going to do any work because it's not going to move it at all, nor is it going to slow it down. It's doing nothing as far as this displacement is concerned. Now, the other one, this horizontal bit of force, you bet that does work. That's doing positive work. So our horizontal force does positive work. Now, I'm sure that you don't want to remember this, but if this is an angle of theta, then that horizontal force is my big force times the cosine of that angle. And we have a new way of talking about work. We have a new way of talking about work when we're at an angle. In this case, my work is going to be not F, but F cosine theta, the part of my force that's doing work, times the displacement. So a better way to talk about force is that, talk about work is that work is force times the displacement times the cosine of the angle in between those two. Now that's going to give us three things to look at. Okay, the first one is positive work. Okay, with positive work, and we already kind of said this, force and the displacement are in the same direction. The angle between them is 0. Cosine of 0 is -1. That's where we get positive work from. The second one, negative work, is when we have an object and the force is in the opposite direction of the displacement. In that case, the angle is equal to 180 degrees. They're still parallel, but they're in exactly the opposite direction. When that's the case, the cosine of 180 is -1, giving us negative work. Okay? And then our third case is when work is equal to 0. In that case, I have my object, I have my force on the object, force, but the displacement of the object is at a 90-degree angle to the work that's being done. Now if we take the cosine of 90, that gives us 0. So the possibilities that go with that, let's erase all this stuff. So cosine of 90 is 0. So we get positive work when our force is in the direction of the displacement. We get negative work when the force is opposite the direction of the displacement. We get 0 work when the force is not in the direction of the displacement at all. And we have to use this cosine theta thing to show us all of that, but along the way, with this cosine theta, if we run into a force that is partially in the direction of our displacement and partially not in the direction of our displacement, we only use the part of that force that's doing work. We don't care about this other part. We just care about the part that's doing work. Now, if we get rid of all this real quick, and go back to drawing. Let's say you're holding a book. In that case, the force is up. You're pushing up on the book with your hand. We're going to say that this thing's a hand. Now, if you're just holding that book, it feels like you're exerting effort. It feels like you're doing something. According to our definition of work, because you're not moving, you're not doing any work, because there's no displacement. Now, let's say you take your book, or your hand, you hold your book, you move it. You walk across the room. But even though your delta x is that way, your force is straight up. These two things are not in the same direction. This force is not accomplishing this delta x. So that force does 0 work. Now, the last thing we said we were going to talk about was graphs. So, let's draw our axes. And let's say that this one is force as measured in newtons, and this one is position as measured in meters. Now, if our graph looks like that, okay, that means as we move forward, we're pushing with an increasing force. So if we look at this graph, look at the area under the graph, right here, to calculate that area, okay, we have to take our force times our displacement. This is a little bit different than work equals F times our displacement, because my force is changing, so I can't quite use that anymore because this isn't a constant force. So with this graph we have a force that changes, but I know in general here that any area is going to be the quantity of force times the quantity of distance. It's going to give me displacement. So the area here is equal to the work. So in this case it's a triangle, so it's 1/2 base, my delta x, times that final force. Because it's a triangle. Now, if we had all sorts of different shapes, we could do all sorts of different things with it. The only two things we're going to really have to worry about is a triangle and a rectangle. That's then our introduction to work.